Okay, Shabab, some people told me that the previous video, maybe the simulations did not appear on the screen. That's why I'm going to repeat this part of the simulations. Okay, let's go back to the schematics or the circuit once again. Okay, I'm going to put my sinusoidal source. I'm going to move my sinusoidal source here. Let's click on it until it is red, then we can move it. Okay, we'll click on the attributes. Let's set the DC and AC. We don't have to set them. V offset, I'll put it 0. This is the offset. Okay, amplitude, let's make it 5 volt. Save. And then frequency, let's make it 1 kilo. Save. Then we click OK. Then if we simulate, we go to the transient setup analysis, transient. We can simulate, since the frequency is 1 kilo, then the period will be 1 millisecond. Then we can simulate, it's enough to simulate 3 milliseconds, 3 periods. Okay, and in each millisecond, we can choose the step size, the step ceiling to be maybe 1/1000 of the period. So if the period is 1 milli, then maybe we choose 1 micro, 1 U, 1 microsecond as the step size, so that we have 1000 point in each period. Okay, that's enough. Then we click OK, close, and then we go to simulate. This button is for simulate. Then I hope now you can see it. I'll move my picture down a little bit. Now you see that we are plotting some curves with the time. In order to plot a curve with the time, you have to add a trace. For example, we can say add the voltage of L2 terminal 1. Okay, we'll see that we have the voltage of coil number 2, terminal 1. Maybe we add another trace, the voltage of the capacitor C1 terminal 1. This is the voltage of the capacitor. If you want to add any other trace like a current or any other multiplication between a current and voltage, for example, we can add the multiplication of the IR or IL1 times we write times by ourselves, VL1 maybe. There is VL1 here, by the way. V1 L1, this is the voltage across the L1. We'll find that we get this blue curve. This is the multiplication between the current of the inductor times the voltage of the inductor. Taban, it's very small because we are plotting it on the same scale as the voltage, and maybe this I times V, it will be in the range of milli. But if we remove the other curves, we'll find that the multiplication curve will appear, and the I times V. So you can multiply. You can multiply any two parameters and you plot them. You can add, you can subtract, you can do any operation and plot this operation. And also you can plot currents, for example, I of L2. Okay, it will appear like this. So similar to the DC sweep, we can do anything. So this is for the sinusoidal source. For the V pulse, as I explained in the video, we can go back to the schematic. We can replace this sinusoidal source with V pulse, where V pulse can be used to generate a periodic rectangular wave, or we can use it to generate also triangular wave. So here, DC and AC, we don't touch them. V1 is, as we agreed, this is the low level. We'll put it 0. V2 is the high level. You have to save after each parameter. Let's make the high level 5 and save. Delay, we'll put it just for demonstration as 1 millisecond. Okay, and then this delay means that the waveform will be delayed by 1 millisecond. T rise, we'll put it for now very small, 1 nanosecond or 1 microsecond. 1 micro is U. Okay, my 1 microsecond. The fall time, we'll put it also as 1 microsecond. This is the practical rise time and fall time, as I explained in the previous Video, the pulse width, this is the width of the high level. So you know that the rectangular pulse, it has a high level and then a low level, 5 volt up and then 0 down. This is what we chose here. Okay, so the pulse width is the width of the high level pulse. So maybe we can choose it here to be, for example, 2 milliseconds. And the period, of course, the pulse width has to be smaller than the period, right? So the period here, maybe you can choose it to be 5 milliseconds. Okay, so we choose the pulse width to be 2, the period is 5. This means that the high level will stay for 2 milliseconds and the rest will be for the low level, okay, which is 3 milliseconds. And then we click OK and we go to simulate. And we are going to show this point, the voltage of this point, which is the same as the voltage of the source. So we are going to simulate now. Then, but we have to change something in our simulation. We have to change the simulation time because the period now, our period is 5 milliseconds. So we need to show more than one period. So maybe we need to the analysis. We need to go to the analysis transient and we show more than 5 milliseconds. The period is 5 milliseconds here, so maybe we show 2 periods, 10 milliseconds, okay? And then we simulate again. Now, let's plot now VR11, okay? And we'll find that we got here a periodic square wave. Notice that the delay is 1 millisecond. This is the delay. The waveform started delayed by 1 millisecond. If the delay was 0, the waveform would have started at 0, high level and then low. But here we added a delay of 1 millisecond. We can remove it. We can put it 0, but I added it for the purpose of demonstration. Then here is the pulse width. The pulse width goes from here to here. As you see, the pulse width is 2 milliseconds because we set it to be 2 milliseconds. Then the period, the whole period is from here up to here. The whole period is 5 milliseconds. It goes from 1 up to 6, from 1 up to 6. So the whole period is 5 milliseconds, okay? The rise time and the fall time, both of them, they are very small. That's why we don't see them. But we can use the rise time and fall time to generate a triangular wave, as I will show you now. So if we go back to the schematics, change, let's go, keep 0 and 5. We can, by the way, change the levels. We can make it -2 and 2. We can make it any other level. If we change time delay, let's make it 0 for now, 0 time delay. Okay, then the rise time, let's choose it to be 1 millisecond, 1 millisecond, and the fall time also will make it 1 millisecond. Why I make it 1 millisecond? Because this is exactly half of the pulse width. So if the pulse width is 2 millisecond, actually we'll make it smaller now. We'll make it in the range of nanosecond. If you choose the rise time to be 1 milli and the fall time to be 1 milli too, then you can generate a triangular wave that is 2 milliseconds, 1 milli up, 1 milli going down, and you make the pulse width in the middle very, very small. So we choose here the rise time to be 1 milli and the fall time to be 1 milli. And the pulse width, let's make it in the range of 1 nanosecond. Don't put it 0. Don't put the pulse width 0 because this may cause a problem, but put it very small. So if the pulse width is very small, this means you will get the rise time 1 millisecond, the fall time 1 millisecond, and between them, the pulse width is very small, it will not appear. So it will appear as a triangular wave. In this case, maybe if we keep the period, if we keep the period to be 5 milliseconds, we get a triangular wave, but separated. The triangles will be separated from each other. Let's try this. If we do simulation now, simulate, and then we show the trace VR11, you'll find that we get a triangular waves, but they are separated. Why they are separated? Because the period is 5 milliseconds. We made the rise time to be 1 millisecond, the fall time to be 1 millisecond, and the pulse width in between to be very small in the range of nano. Then this is our pulse, and then in the remaining period is 0. Assume that we want triangles to be stick to each other. To stick to each other, what can we do? We need to change the period to be 2 milliseconds. If you change the period to be 2 milliseconds, you will get a triangular wave as required. That's it for this part of simulations. You can do any process. You can use cursors. You can change the also the axis to be log or anything that we learned in the DC sweep. You can do it here. Okay. So that's it for this part. I will stop recording, and if you have any questions, you can ask me online. Okay.